You know that little padlock icon you see in your browser? Ever really stop to think about what it means? Or how your bank is so sure it's you logging in and not somebody else? Well, it all comes down to this incredible, invisible architecture of trust, built on some really, really clever math. So today, let's pull back the curtain and demystify this whole world of digital signatures and key management. And hey, this isn't just about making our online shopping a little safer. This is a huge deal. As this quote from India's national cybersecurity policy shows, building trust and confidence in electronic transactions is a massive national priority. It's what our entire digital economy, our e-governance, and our finances are built on. The stakes are just incredibly high.
And that brings us right to the core problem, doesn't it? I mean, in the real world, we have things like handwritten signatures and sealed envelopes. But online, everything is just data. Ones and zeros that can be copied perfectly, changed without a trace. So how on earth do you prove who you are? And how do you prove that what you sent is exactly what was received? So here's our game plan for today. We're going to start with that trust problem, then look at the magic two-key system that started it all. We'll see how digital signatures work, how certificates act like a passport, and then figure out how we can share secrets with something called a digital envelope. It's all going to come together to show you the real backbone of online trust. Okay, let's get into the absolute foundational breakthrough that makes all of this possible. It really is like magic, the magic of having two keys. You see, for centuries, encryption was pretty straightforward. You had one secret key to lock something, and you used that same key to unlock it. We call that symmetric encryption. It's fast, it's efficient, but it has one giant glaring problem. How do you get the key to the other person securely? If you can get the key to them safely, you could have just sent the message that way. Asymmetric cryptography completely flipped this on its head by creating a pair of keys that are linked together mathematically. And this is the part you really have to get. You create a key pair. One is your public key. You can give this to anyone. You can post it on your website. You can shout it from the rooftops. It doesn't matter. The other key is your private key. You guard this one with your life. You never, ever share it. And here's the magic. Anything that gets locked or encrypted with your public key can only be unlocked by your private key, nobody else's. This completely solves that key sharing problem. It's brilliant. Okay, so we have this powerful new tool, this two-key system. How can we use it to prove who sent a message, and just as importantly, that the message hasn't been messed with? Well, that's where digital signatures come in. And what's cool is they basically work by using that public key idea, but in reverse. Now, first things first, let's be absolutely clear. A digital signature is not a JPEG of your handwriting. It has nothing to do with that. It's a chunk of cryptographic data that acts like a tamper-proof seal. And its job is to do two things: verify authenticity, yep, this came from you, and verify integrity, yep, this message is exactly as you sent it.
So how do you make one? It's a simple two-step dance. First, you take your message and run it through a process that creates a unique digital fingerprint. We call this a hash. The cool thing about a hash is that if you change even one single comma in the original message, the hash changes completely. Then you take that small fingerprint and you encrypt it using your private key. That little piece of encrypted data, that's your digital signature. Now, when someone receives your message, they can verify it. And this is where it all comes together. They use your public key, which is available to everyone, to decrypt your signature. That reveals the original hash you created. Then they take the message you sent and they create their own hash of it. If the two hashes match, it proves two critical things. One, since their public key worked, it proves only you could have created it with your secret private key. And two, since the hashes match, it proves the message wasn't changed by even a single byte along the way. Okay, that's fantastic, right? But wait a minute. This whole thing relies on me using your public key. How do I really truly know that the key I have actually belongs to you? What stops a bad actor from just creating a key pair and yelling, "Hey everyone, this is Amazon's public key"?
This is the impersonation problem. It's a huge potential flaw. If you can't trust that a public key belongs to who it says it belongs to, the whole system of trust just crumbles. So, how do we fix this?
The answer is something called a public key certificate. And honestly, the best way to think of it is as a digital passport. You go to a trusted third party, we call them a certificate authority, or CA, and you prove your identity to them. They then issue an electronic document, this certificate, that binds your identity to your public key. And to prove it's legit, the CA digitally signs the certificate themselves. So
If we were to crack open one of these digital passports, here's what we'd find. You've got the subject, that's the name of the owner, like Amazon.com. You've got their actual public key. You've got the issuer, the CA who signed off on it, and it has an expiration date, just like a real passport. But the most important part, the absolute linchpin, is the CA's own digital signature at the bottom. Your computer already has a list of trusted CAs, so it can check that signature and say, yep, I trust the CA, so I trust that this public key really does belong to Amazon. All right, so we've solved identity, we've solved integrity, but what's left? What about plain old privacy and confidentiality? What if we just want to send a long, secret message that nobody else can read? We need to solve the eavesdropping problem, and we've got to do it in a way that's actually efficient. So we run into that trade-off again. Asymmetric public key encryption is super secure, but it's slow. It takes a lot of computer power. It's not something you want to use to encrypt a 2-hour movie. But that old-school symmetric encryption, it's lightning fast. Its only problem was that pesky key-sharing issue. So what if we just use them together? Get the best of both worlds. And that's exactly what a digital envelope does. It's this beautiful, elegant hybrid approach that gives us the raw speed of symmetric encryption for all the heavy lifting, but with the rock-solid security of asymmetric encryption to protect the most important part, the key itself. Here's how it works. It's really clever. Your computer generates a brand new, random, one-time use symmetric key. We call it a session key. It uses that super fast key to encrypt your whole big message. Then it takes that tiny little session key and encrypts that using the other person's public key. You then send both things together, the big encrypted message and the little encrypted key. When they get it, they just use their private key to unlock the session key, and then use that session key to unlock the message. It's fast, simple, and incredibly secure. So we've looked at all of these different pieces of the puzzle: digital signatures, certificates, envelopes. Now let's just step back and see how they all lock together to form the real backbone of the trust we have online every single day. So let's just recap those 3 pillars. Digital signatures give us authenticity and integrity. We know who sent it and that it's untouched. Public key certificates give us identity. We know who owns the key. And digital envelopes give us confidentiality. We know only the right person can read it. You put those 3 together, and you have the foundation for almost every secure thing you do on the internet. And remember that little padlock we talked about right at the start? Well, next time you see it, you'll know exactly what's going on. Your browser is performing this exact dance. It's checking the website certificate, it's using public key crypto to create a secure session key, and then it's using that key to encrypt everything. This invisible architecture is working for you, thousands of times a day, without you ever having to think about it. Which brings us to one final thought to leave you with. This system has been incredibly successful, but our world is changing. With AI getting better and better at creating convincing deepfakes and our lives becoming more connected than ever, will these pillars still be enough? What's the next great challenge for digital trust? That's the question we're all going to have to answer.